Now I said we are going to revise the paper. That is the paper one. So I said everybody should have his own paper. I think everybody has one. And then we are going to look at the questions, those ones that I feel maybe we need to review and how to answer them. Then from tomorrow, we continue from where we left the inelastic coalition, the types of coalition. Now, question one, are we having the paper? Question one was testing on the micrometer, screw gauge. You can use the screen. Whiteboard. Share. Now, question one, we were having a micrometer screw gauge which has a negative error, and for that case, we know when the error is negative, we always add it, and if the error is positive, we usually subtract it from our measurement. So first we get the value, and I mentioned this, that a micrometer screw gauge, for micrometer, we usually have the two types. We have the one with 50 division, and we have the one with 100 divisions. That is on a thimble scale, because we have the main scale, which is the horizontal part, and then the curved part. So usually we have the main scale here on top, and then we have the thimble scale here, which usually the line that is joining with the thimble scale, that is usually where we now read it. So the one here, this one here, is the thimble scale, which will have either one, we have the one with the 50 division, and then we have another one with 100 division. So for like this case, if you look at our thimble scale here, it is we have 45 and then 0. That actually means that we are having a half thimble scale division or a 50 division. So it is not 100. And if it is a 50 division, then you are just going to have if we have the 50 scale division, if for example this is at 1, then we have 2 here. Usually there is a lower scale which divides this into 0.5. That is, it means that will be 1.5 there. So there is always a half scale below it. And that is what our thimble scale here is having. So for our case here, we have a 50, the fifth here, then we have the rest everything. So we have, we have the 5, then we have 1, 1, 2, then we have the thimble scale ending there, and then we have just below we have 1 division here, and then here we have 45. Then from there 1, 2, 1, 2, 0, we have 0 there. So actually where 0 stands, that means from 45 we are heading to 50, or like it is from 45. So at this point that is 45, this is 46, 47, 48, 49, and actually 50 is here.
Okay, your voice not clear.
Yeah? What is not clear?
Can't hear you well, Manu.
You can't hear me well?
Yes. Your voice is too low.
Are you now getting me?
Yeah, now you're okay.
I'm okay. Yeah, so I've said that that scale is a 50 division scale. So if you look at that, it means just below 5 on the lower sum point. Then we there must be a point there. There's another one here, and then there's another one. So if you read the main scale, that will be 5, then 6, 7 will be there. So our value is not going to be more than 8 because you can see 8 is not there. So there, our reading must be lying between 7 and 8. So there, if for now you go to the lower scale, because I said this is going to give us a half division, already you can, at this point here, at this point, then that means up to there we can read 7.5. So we are going to say our main scale is going to give us 7.5. And remember, all the unit for a micrometer screw gauge are in millimeters. So that is 7.5 millimeter. And then we go now to the thimble. So that means the remaining part from here, this point here, that is the value that we are going to get from the thimble scale. So if you look, we look this main line here, the value it is coinciding with on the thimble scale now is this point here, which if you read, we have 45 there, we have 46, and then we have 47. So actually, our thimble scale gives us a 47 division. So we say a thimble scale, is going to be, that is 47 division. And we have what we call the least count. So the least count, usually for a thimble scale, a thimble scale give us up to the second division. So we just say times 0.01 millimeter. Now, if you add the two, you're going to have 7.5 plus this one. If you multiply, that will give you 0.47. So now if you add that, allow me to use this upper part here. If you add that, that gives you 7.5 plus 0.47, and that will now give you 797. So we end up with 7.97 millimeter division. Question? Any question? Are we okay? Are we okay?
Yes.
Fine. Question two, that question is testing on forces. And wherever actually that is on a friction and is a topic that you're going to do, but you did it briefly in form 1. Now, whenever you're going to have a body and that body is landing on a surface or is on a surface, there is always the weight of that body which is going to act down due to gravity, weight due to gravity, which we usually give mg. That is the force due to the weight of gravity. Then wherever there is a force acting downward or when the body is landing on an object, there are going to be a normal reaction that which is usually equal R, which is usually equal to mg. Sorry, this is mg. This is mg. That is mg. So, and then if there is a force, unbalanced force acting on that body, usually, for example, let's say there was an unbalanced force acting on that body, or if you apply a force on that body, if it is moving, then let's say we're going to have the action force there. Then if the body is moving towards the right, there's going to be an opposing force or a friction force which will act in an opposite direction. That is the friction force. So most of you were just indicating the friction at this point. The friction force, remember, it is acting at the point of contact. So we have the surface here, that is a rough surface here. So you are supposed to put your arrow down here and not up there, because you're showing the point where it is acting. So we have the force acting on that other side. Now with our exams, they're usually a funny way of setting exam. This kind of question, somebody can set it and then just have your body and then we have the surface. Then you just tell you, for example, we have poured some liquid. Maybe it could be water or it could be mercury here. Then you have a force acting there. We have the friction down there. Then we have the reaction. and then we have the action. But the fact that we have a fluid at this point also means that they are going to be, that is adhesive force. That is the force that is going to be attraction between the block and then with the fluid, or which can be water or mercury. So for that case, the arrow was supposed to be down there and not up there, and in an opposite direction to the direction the body is moving. Question 3, I think. Okay. Question 3. The question is testing on the pressure, and then it asks you to determine the force necessary to keep the system in equilibrium. This is from the Pascal principle of transmission, of equal transmission, which says that if we have a body at this point here, or connected, and there's a fluid inside, provided that fluid is incompressible, we have, this one has area 2, and then there's a force it is producing, force 2, and then we have force 1 acting on area 1 there. Then we're just going to have pressure transmitted at this point, P1, and the pressure transmitted at that point, P2, are supposed to be equal, provided they are at the same level. So pressure 1 is equal to pressure 2. And pressure 1 we know is that is force over area, which is F1 over A1 should be equal to F2 over A2. Now what we are looking for, is determine the force F needed. So the force F, this is the force F, that is we're looking for F1. So F1 is just going to be equal to F2 over A1, which, if you now multiply both sides by A1, if you multiply both sides by A1, multiply by A1, A1 and A1 will go. So you end up with F1 equal to F2 over A or 2. Sorry, this was A2 multiplied by A1. Now, so you already have the formula. Then you go. Can you hear me? Then you go to the question now. They're talking about the diameter of the cylinder A in figure 3 is double that of cylinder B. So A1 is I think Mr. Mwaji, let him hang. Come on, let him hang. So our area 1, if we say let our area 1 be A, then our area B is double area, and then area 2, we are being told that the cylinder A in the figure is double that of B. So if A is that, B will be A over 2, because A is the maximum one. So we are having now determine the force necessary to keep the system in equilibrium. We have the force 2 being equal to 10 newtons. So substituting there, we are going to have force 1 is equal to 10 times area 1, which is A, over area 2, which is A over 2. Now from there, that just become 10 times A times 2 over A. And A goes, and then you get the force 1 to be 20 newtons. Remember, always in physics, you have to indicate the units. So up to there, so you are supposed to get the 20 newtons. Okay. Question 4. That was a theoretical question. Factors that affect the rate of diffusion. We have the size of molecule or density of the molecule. That will be a condition that the larger, that is the larger the molecule, the lower the rate of diffusion. And then the smaller the molecule, it is so easy to be carried away by the fluid. Also, we have the temperature. Temperature is also a factor that affects the rate of diffusion. And then we have, okay, with the temperature, if you increase the temperature, we know that has to do with the kinetic theory. So increase the temperature, the kinetic, the molecule vibrate more, and that is, there are higher chances of moving away from the source. Then we have diffusion gradient. That is diffusion gradient. Diffusion gradient, that means the difference in concentration of molecules between two regions. So if I have, okay, so diffusion gradient, that means the difference in concentration between the two regions. We have region A and region B, and then we have region C. Let's say here we have 5 molecules. Here we have 1 molecule, and here we have 4 molecules. Now, if you look at this, you'll find that at region B, the molecules are more concentrated than region A. And then than region B. But the region that has the least concentration is region A. So it means that there are high chances that molecule will move from region B to region A faster than from A to B, because here we have a very low concentration. So the difference in concentration, that is what we call the diffusion, the gradient. So the higher the diffusion gradient, for example, this point I'm going to say here, we have a higher diffusion gradient because the difference in number of molecules is wide. But here we have a lower diffusion gradient, the difference. So we expect more diffusion here than there because of difference in concentration of molecule. So those are majorly the 3 factors that affect diffusion, which we look on under physics. We have the others also in biology, but here now we are concentrating on physics, which majorly there are these 3 that we look at. Question 5. Question 5 is asking, show a simple fire alarm. We have the terminal, we have mercury, we have the bell. Then explain how the alarm functions. I think this is the question somebody was asking yesterday. I think that was Shafi and Zubair about the question of explaining. I said, like, if you look at this question, it is carrying 1 mark. So it means your explanation should not have more than 2 lines if it has to go. Now we are going to look at the key points. How do we answer this? So we have our bell here. Then we have our mercury, somewhere mercury here. And then we have the terminal, which is just hanging somewhere here. We're having the terminal at that point. Now you can see up to the point where mercury is, and where the terminal is, there is that space, meaning when mercury is at this position, the circuit is not complete, or there is no completion of the circuit. So actually what mercury is going to do here is to complete the circuit, because we know it's a liquid that is a good conductor. So if you look at that diagram, you will find that it means we know mercury has a capability to expand. That means that during fire, for example, for this case, we expect the temperature to rise. And if temperature rises, we expect the mercury to rise also. So it will come up to this point, high at this point, then it will make contact with the terminal, and if it make contact with the terminal, then it will complete the circuit. And if the circuit is complete, then the bell will ring because the current is flowing through. So the first point, if you are describing this experiment, first thing, mercury expand. That is what we look at. And that was going to give you a half a mark. Just mentioning that mercury expand, that is during fire, because the temperature, mercury expand, and the reason behind that is because the temperature is rising. Mercury is expanding because of rise in temperature. Then, once the mercury has risen, it is going to make contact. So the next point is going to be contact. There's going to be a contact between mercury and the terminal. And if there is a contact, circuit will be complete. Circuit will be complete, and then current will flow, making the bell to ring. So if you look, if generally I'm going to mark the question, or whoever is going to mark the question is going to look at mercury, which is going to expand due to temperature rise. Then we're going to look at do you have the word contact somewhere? Because there must be contact and completion of the circuit. So from that point now, you can struggle with the English and then make a sense. So now, what are we supposed to say here? We will say during fire, mercury expand, up to there, give you a half, completing, making contact with the terminal, completing the circuit, hence the current flow, making the bell to ring. You can see from my statement, if you were to put that in words, it is not going to be longer than 2 sentences. Okay? Question number 6. Question 6, the figure 5 shows 2 identical containers, container A and container B, containing equal amount of water and identical ice block. One we have, container A has floating ice, then we have hot water, then one has our ice. Okay, our ice always will float on water. That is from the anomalous expansion of water. So if you look at that, ice has been wrapped in the wire gauge, and then that wire now will make that ice to sink. That question already from it, if you look at it, it explains it is a conventional current question. So we have the ice there, and then we have ice here wrapped in a wire gauge. What the wire gauge, what it does is to make the ice to sink, and also it has also a good conductor, so it is going to absorb some heat from the hot water and then make ice even to melt faster. That will be another function that it does. Now from here, if you go back to the conventional current, we know that if we are heating a liquid from this bottom here, what usually happens is that the hot part, the hot molecules, usually expand, and then if they expand, they become less dense, so it will move up. And the one that was up here is is denser, so it will come down. So when it comes down, also it gets heated, and the one on the top is losing some moisture. So with the time, also it will go up. So that's what ensures the conventional flow. That the hot goes to the top, the cold come on the bottom. Now, if you look at these 2 diagrams, this one here, it means the water at this point is going to be heated, and this one here, the water at the water molecule at the lower point are going to be heated. So from here, we know when these molecules get heated, they become less denser. For case A, these ones which are less denser, they are on the top. So they can't come to the bottom. They'll just remain on the top. And for this case here, the molecules which are at this point and they are less denser, they will go up, and the one at the top here will come down. Now, so we expect a conventional current at this point. At this point. Now, at the here, we are not going to have a conventional current because the ice here is going to melt and then it will remain at the top. So the question is asking, state with the reason which water cool faster assuming the gas absorb negligible heat. This one is going to have a conventional current, so we expect this one to cool faster than this point, because what is going to happen? Oh, sorry. We expect, just a minute, the cold ice. Oh no, we expect the conventional current. We expect this one, which is being heated, and then they melt. It cool the liquid below, and then it will fall down. Yeah, it will. The water which was at the top here and has been cooled by ice will move down, and the one for this case, the one which was at the bottom here is going to be cooled, but it will remain at the bottom. So that means the one at the top here is not most likely to cool down. So for that case, we expect this one to cool faster because the cold one will come to the bottom, the hot one will go up and also get some cooling. So A, it will cool faster than in B. Next, that is question 7. The figure 6 shows a suspended uniform meter rule in equilibrium when a mass of 50 grams is hung at the 0 mark. Determine the tension T in the string. Determine the tension T in the string. So we have the string here. We have a meter rule there. We have a 50 grams hung at that point. We have the suspension when mass of at a 0 mark, then when a mass of, we have a mass that is at 0 mark, and then at the 10 centimeter mark, we have the tension here. Now, our meter rule is a uniform bar and we have not been given its weight. So the first assumption we make here is that the weight of the bar is negligible, or we are not going to consider it in this calculation because it is not, we have not been given. So from there, we are going to, we have the 3 points. We have a point there where the weight is acting. We have the point where the tension is acting, and then we have the end of the bar. Now I'm going to take my moment from this point, this end here. Now taking moment means you're going to make it, okay. If you are going to take your moment from that point, it means you're going to make it the turning point. Now, if you make it the turning point, then you consider the two forces. Assume there is no tension force, and this bar or the meter rule can turn from this end point here. Now, if only the load of 50 grams was acting on it, we expect this load to move. We expect the bar to move in anti-clockwise direction. And if you assume there is no weight and only the tension is acting on this bar, which is acting upward, we expect this body to move in clockwise direction because the bar will move up. And so from there, we know that clockwise moment is equal to anti-clockwise moment. Now, the 50 mass is acting at the 0 mark. So if you consider its distance from the turning point, that is 100 centimeter or 1 meter. The tension is at 10 mark from the 0 mark, but if you calculate now, that means the remaining part is going to be 90 centimeter. Now, clockwise moment is caused by the tension. So we're just going to say tension times the distance, change into meter, that is 90 over 100 should be equal to anti-clockwise moment, which is caused by the mass of 50 grams. That one, if you convert to Newton, that is 0.5. newtons times the distance which is covering, which is 100. Now, up to there, we are going to have our tension times 0.9 is equal to, that is 50. So T is equal to 50 divided by 0.9. So you get your tension to be, calculation, if you calculate that, you get 55.5 recurring, and 5555. So we just make that. I said you just show the whole value first, then you round off to 2 decimal, 55.56 Newton. So up to there, I think we'll continue with the rest of the question still, but tomorrow we have to go on with the syllabus. So, I think up to there we have revised up to question 7. We also create some time. I'll also try to make some video of the paper and then send it via the WhatsApp, so we can also move on. From tomorrow, we will continue with our notes. That is from the inelastic coalition. Then we do the friction. And then part of these notes, I'm also going to send the, I'll be giving notes, and then I'll be sending a video trying to explain what you're supposed to do as you copy them, so that we can also get time. You see, we have wasted a lot of time online. So I'll also be doing some videos and try to explain some points. Then you can also get to watch them and copy the notes, so that when I come back, we move, because we have very limited time, which is the only 40 minutes. Unless there is a question. Any question concerning the paper? We are going to revise all the papers, so we just go systematic. We are going to revise paper 1, paper 2, and even the practical. Any question? Just carry up your hand. Yes, Shafi.
Yes, Mwalimu, I have a question on concerning number 6.
Number 6, yes.
Mwalimu, in B, container B,
Yeah.
wire gas has been used,
Yeah.
unlike container A. So what's the importance of using that, the importance of wrapping the ice with wire gas?
I started by explaining that, and I said that wire in ice, according to the topic you did in Form 1, and the molar's expansion of water, ice is usually less denser than water, so it usually floats. Now, the wire gas was used purposely here to make the ice sink, because ice on itself cannot go to the bottom, cannot sink to the bottom of the container. So the purpose of the wire gas was to make the ice sink. That is the main role if you look at the question. But also this the wire gas here, because the good conductor, is also helping to distribute the heat. So that could also be a reason why the two experiments are not similar, or like the one is the control experiment of the other. So the main role here is to make the ice sink. We don't consider it as, now we assume that it is not contributing anything on the heat distribution here.